Welcome to A-Star Science, part of our Chemistry A-Level series. Today we're going to be talking about the topic cells and half cells. This is part of the electrochemistry unit. Electrochemistry refers to the chemical process of transferring chemical energy to electrical energy. So in other words, batteries. You already know about many of these topics because in GCSE you would have recalled seeing a symbol like this, which represents a cell, and you would have recalled seeing a symbol like this, which represents a battery. Okay, a battery. So you are already familiar with many of these topics, and it's a topic that's very, very important in today's world, where many of the portable devices that we use, such as mobile phones, the headphones and earbuds and earpods that people use, things like drones, and even, of course, electric cars, solar cells, they all depend on battery technology. So this is a very, very important topic for those people that want to get involved in that particular industry. So first, let's look at the term cell, which from GCSE was represented like this. Some people call it a battery, but a cell in electrochemistry is made up of two half cells. So right now I'm going to draw a half cell, and I'm indicating this as copper. So let's say we have a piece of copper metal, and this solution will be copper sulfate. Now we know that copper sulfate has the ion Cu2 plus. Cu2 plus. So that means that the oxidation state of this copper, the charge is 0, the overall charge, but this copper is 2 plus. This is what we call a half cell. And it is when you have two different oxidation states of the same element. So in this case, that would be the copper. So the copper has an oxidation state of 0 when it's an elemental copper, that one at the top in red. And as a solution, an aqueous solution, it has an oxidation state of 2 plus. That means in that solution, you're going to have two different oxidation states of the same element, okay? And that means we're going to get a movement of electrons. So what happens to make this now? That's a half cell, but how can we make this a cell, a full cell? So let's continue with our diagram, and let's put that beaker back and put the copper sulfate solution inside. So this is copper sulfate solution. And next to it, if we drew another beaker, and in this one, we'll put zinc sulfate, and we'll put a piece of zinc metal here. We now again have another half cell. If we connect these two half cells, like so, and we put a voltmeter in between them like that, we're going to start to develop what we call a full cell. And that's what's indicated actually by the GCSE symbol. So this will be a full cell, but we need a circuit to be created. Notice we only have the pathway for the electrons to flow here like that. So we need to create a circuit, and we do that in electrochemistry by using what's called a salt bridge. So that will be the salt bridge. So the salt bridge will consist of some sort of solution, ionic solution, let's say sodium chloride, and that will allow the movement of mobile ions, not electrons. Mobile ions can move from the salt bridge or through the salt bridge from one half cell to the other half cell. Now, you should be asking, well, which way are the electrons going to go? I know that in this case, that the electrons actually are going to go this way. I think I'll do that in red. This way, like so. But there's a reason for that, and we're going to look at that in the next stage of this video. Just to summarize again, what we have here is two half cells. Here is one half cell. And here's the other half cell. And together, they make an electrochemical cell, a full cell, electrochemical cell. Now, remembering in the first part of the video, we had two half cells. One had copper in it. So that was the one with copper and copper sulfate, which acted as the electrolyte. And then between that, we had a voltmeter, which is going to measure the potential difference. And then we had another beaker over here, and we put a piece of zinc metal here, like so. And we had an electrolyte here of zinc sulfate, like so. And then we used a salt bridge, like that, which we had sodium chloride as an electrolyte to connect them. And we were trying to figure out which way the electrons would go. Well, first we need to think about where the electrons come from. So to do that, we can write a half equation. If we know that we have, for example, copper 2+ in the electrolyte, then we also have copper on the other side. That means that we can add electrons to form the elemental copper. In the other half cell, we have zinc 2+, and that's going to go to zinc metal. And if we add 2 electrons, we know that we can get elemental zinc. But we need to determine which one is going to get electrons and which one is going to give electrons. And for that, we're going to use the chart on the left, which has what's called the standard electrode potentials of each half cell. And we'll talk about how they derive these in a minute. So these are the standard electrode potentials of the individual half cells. So if we look and we can find the one for copper, which is here, that has a standard electrode potential of plus 0.34 volts. And the zinc one, which we can find here, has an electrode potential of minus 0.76 volts. So in this case, we can see that the zinc has the more negative electrode potential. That means that zinc is going to be our supplier of electrons. So I know that the electrons are going to travel in this direction from the zinc, like so, around the circuit. Now, that means I need to change this equation at the bottom, and I need to reverse the zinc equation, because the zinc now is going to lose electrons and become zinc 2+ and give up 2 electrons. So effectively what you have is the zinc providing the electrons, which are going to go to the copper 2 plus, and that copper 2 plus then is going to form the copper by taking up the electrons, like so, okay? So this is how a voltage is formed. A voltage is formed because, sorry, a current is formed because of the movement of electrons between the half cells, which is then facilitated by the movement of ions to make sure that that is balanced. Okay, so the ions have to move, the mobile ions have to move that way in order to make sure that the electrochemical balance is correct between the two half cells. Now, what's very important to understand is that when you have two half cells, to find out which one is the most, is going to give the electrons, you simply look at which standard electrode potential is the most negative. It does not have to be a negative charge. It's the most negative. So for example, even though lead 2 plus is plus 1.67 volts and silver is plus 0.80 volts, silver in this case will be the half equation that produces the electrons. So we would write the silver half equation like so. And the lead half equation would take up those electrons to form lead. And so these electrons would go that way. Obviously, we would have to balance it to make sure that there are two electrons for the lead to uptake in this process. So we know that the top process is an oxidation reaction where they're losing electrons. It's going to be losing electrons. And the bottom one is reduction, where it's gaining electrons. So in this case, the silver is going to act as the anode because that is where the negative electrons are going to come from, and the lead is going to act as the cathode. Because that is where the negative electrons are going to be taken up. Now, when we have two half cells together, again, if we create two half cells, in this case, we'll use zinc here and electrolyte of zinc 2 plus, so zinc sulfate, and then we'll use this one as copper. We'll put a piece of copper in, like so, elemental copper, and we'll use copper sulfate. We'll have our salt bridge, like so, and then we'll connect the top with a voltmeter, and now we have a full cell. Well, how can we determine the standard potential, electrode potential of this particular cell, meaning what is going to be the resulting voltage of the cell. You'll be familiar with this because when you buy a battery, it normally will tell you what the voltage is. So 1.5 volts or 9-volt battery. And that's because these batteries are made of half cells put together into a full cell, and they generate a voltage. Well, how do we create that voltage? How do we determine what that voltage is? So if we look on our chart, we can see that zinc, the standard electrode potential is minus 0.76 volts, and the copper is plus 0.34 volts. You determine the final voltage by doing the most positive minus the most negative. So in our case, that would be 0.34 volts minus 0.76 volts, which is going to equal to 0.34 volts plus 0.76 volts. And let me add that together very quickly. That's going to give me a 0, a 1, a 7, and a 3. So that's going to be 1.10 volts. So this cell, full cell, will create a voltage of 1.10 volts. Now there's something called the standard notation, chemical notation of how we indicate these cells, because drawing the cells is going to take a long time every time. So how do you do that? So let's do an example of this one, which is the zinc and copper, to zinc half cell and copper half cell. The first thing we're going to indicate with 2 lines is the salt bridge, okay, 2 vertical lines like so. And then I'm going to put the most negative on the right-hand side, which is a zinc 2 plus, and put another line like so. And I'm going to put the zinc on that side. I'll then put the more positive on the right-hand side. I'll separate it, and then I'll put the copper there. Notice that the oxidation states, highest oxidation states, go next to the salt bridge. This is how we write the chemical notation, scientific notation of electrochemical cells. Now, before we look at the different types of cells, half cells, which give rise to the information about the standard electrode potentials, I want to give a brief commentary on what the standard electrode potentials actually mean in regards to reactivity. Now, it's interesting that even though this is A-level chemistry, in GCSE, you would have already encountered a question like this. So, for example, it says, write the 6 metals used for electrode X in order of reactivity. And they give a list of voltages of the cells. Well, what those are, they don't tell you in GCSE, are actually the standard electrode potentials of these cells. And so how do you find the reactivity? Well, you look for the greatest difference between 2 cells. And we know that the cells that have the most reactive, for example, on this chart, is lithium, has a minus 3.05 voltage, standard electrode potential. And on this chart, it's magnesium. It has a plus 2.71 electrode potential. The ones that have the largest voltages are the most reactive. And so how would you make a cell with the greatest potential difference that's going to provide the greatest current? Well, you would take the metals which have the biggest difference. So for example, in this case, we would have magnesium, which is plus 2.71, and the lowest one, which here is silver. And that would provide the greatest difference because silver is very non-reactive. If we were to do our reactivity series, and magnesium is the most reactive on that list. And then we list them in order. So if we look, magnesium was plus 2.71, then that's followed by cobalt. Cobalt next, underneath cobalt is going to be nickel. And then underneath nickel, it looks like tin. And then underneath tin, which is plus 0.48, is copper. And then it's silver. Okay, so that is the reactivity series based on the voltage, with the most reactive being at the top and the least reactive being at the bottom. We know that silver is the least reactive because it's even below copper. It has a minus standard electrode potential. So this is really important to understand where the reactivities come from. And they also link this to redox on the chart on the right, because you can see that the strengths as reducing agents and oxidizing agents are given. So the more reactive the metal is, the stronger it is as a reducing agent, meaning the easier and the more powerful it is at giving electrons to something else. And the ones at the top, they are strong oxidizing agents, meaning they strip electrons away. So this is really important to understand before we talk about the last part of the video, which is the different types of half cells. So the final part of the video, we're going to be talking about the different types of half cells. We already showed at the beginning of the video a half cell where we had a metal ion. So for example, we had copper here, which had a charge of 0, and then an electrolyte here, something like copper sulfate, which has copper here. The copper would have a 2+ charge, and that is called a metal ion half cell, because the metal exists as two separate oxidation states. And you could see that reflected here on the chart. But it says it has a plus 0.34 voltage. Well, where did I get this number from? Well, this number is known as the standard electrode potential and is measured by connecting a half cell like this, a metal ion half cell, with this particular half cell, which is called a standard hydrogen reference half cell. So this is basically a reference cell, and it will give a voltage of 0. But when you're able to connect it now to another half cell, when you connect these two together, you then can generate a voltage, and that voltage is known as the EMF, which is short for the electromotive force. And the electromotive force is the amount of charge, the amount of energy per unit charge generated from a half cell. And that you can measure that again by using a standard hydrogen reference cell. And that allows a list like what you see here to be generated and created for many different metals and different, not just metals, but different states, chemical species, using different half cell arrangements. There's one more cell, half cell, that we want to talk about, and that is the one on the right, which is still a metal ion, half cell. However, you see this one is a bit unique because there's no solid metal. Instead, it uses aqueous solutions, iron 2 plus in this case, and iron 3 plus, as the two different oxidation states, and then uses a platinum electrode, which is inert. Okay, it's platinum electrode, which is inert, so that's not going to interfere with the reaction and create any new products. As the electrode, in order to provide a pathway for the movement of the electrons. So these are the main types of cells, reference half cells, that you need to be aware of. Please do like and subscribe. Leave a comment. Let me know how you felt about the video, and let me know if you'd like me to do any other videos regarding your A-level chemistry.